Welcome to Shri Learning Academy. Let's simplify process scheduling. When we talk about process scheduling in an operating system, we are really talking about how the operating system decides who gets to use the CPU and when. By the time we reach this topic, we already know what a process is, how it moves through different states, and how its information is stored inside something called a process control block. So now the natural question is this. When there are many processes ready to run and only one CPU or a limited number of CPUs available, how does the operating system manage this situation fairly and efficiently? That is exactly where process scheduling comes in. Think about your daily life for a moment. Imagine a single teacher in a classroom and many students who all want to ask questions. If everyone speaks at the same time, nothing makes sense. So the teacher follows some method. Maybe students raise their hands and are answered one by one, or maybe the teacher gives priority to students who have urgent doubts. The CPU is like that teacher, and the processes are like the students. Process scheduling is the set of rules and decisions the operating system uses to decide which process gets the CPU next. In simple terms, process scheduling is the activity of selecting one process from the ready state and allocating the CPU to it. The operating system keeps track of all processes that are ready to execute, waiting, or currently running. Since the CPU is the most important and limited resource, it has to be shared carefully. Scheduling ensures that this sharing happens smoothly, without chaos, and with good performance. Why is process scheduling even needed? The main reason is multitasking. Modern operating systems allow multiple programs to appear as if they are running at the same time. You might be listening to music, browsing the web, and downloading a file all at once. In reality, especially on a single core system, only one process can actually use the CPU at a given instant. The operating system switches the CPU rapidly between processes. Scheduling decides the order and duration of these CPU allocations. Another important reason is efficiency. Some processes are short and finish quickly. Some take a long time. Some are interactive, like typing in a text editor, and need fast response. Others run in the background, like a system update. Scheduling helps balance all these needs so the system feels fast and responsive rather than slow and unfair. To understand scheduling better, imagine a queue at a ticket counter. People arrive, stand in line, get served, and leave. The simplest scheduling approach is like this queue. Whoever comes first gets served first. But what if the first person has a very complicated request that takes a long time, while others only need a few seconds? Everyone behind has to wait. That may not be ideal. So different scheduling approaches exist, each with its own idea of fairness and efficiency. At a high level, process scheduling can be divided into different types based on how and when the CPU is taken away from a running process. One major classification is preemptive scheduling and non-preemptive scheduling. These ideas will later be connected deeply with CPU scheduling algorithms. But here we focus on the process level view. In non-preemptive scheduling, once a process gets the CPU, it keeps it until it finishes execution or voluntarily gives it up, usually by going into a waiting state for I/O. The operating system does not forcibly take the CPU away. This approach is simple and easy to implement. Early operating systems and simple batch systems often use this idea. For example, imagine a printing shop with one printer operator. Once a customer's job starts printing, it continues until all pages are printed. The operator does not stop halfway and switch to another job. If a large book is being printed, smaller documents behind it have to wait. This is non preemptive behavior. In an operating system, this can lead to poor response time, especially for interactive tasks. In contrast, preemptive scheduling allows the operating system to interrupt a running process and take the CPU away even if the process has not finished. The CPU can then be given to another process. This makes the system more responsive and fair, especially in time sharing environments. Think of a call center where each customer is allowed to speak for only a fixed amount of time before the call is put on hold and another customer is answered. Even if someone has more to say, They must wait for their next turn. This is similar to preemptive scheduling. The operating system uses timers and interrupts to regain control of the CPU and decide who runs next. Now, let us talk about scheduling in terms of system goals. Process scheduling is not random. It tries to achieve certain objectives. These include maximizing CPU utilization, so the CPU is not sitting idle. It also aims to improve throughput, meaning more processes are completed in a given time. Another goal is minimizing waiting time and response time, so users do not feel the system is slow. Fairness is also important, so no process is stopped and ignored forever. Depending on the type of operating system, scheduling priorities can change. In a batch operating system, the focus is on completing jobs efficiently, not on user interaction. In a time sharing system, fast response time is critical. In a real time system, meeting deadlines is the most important requirement. Process scheduling adapts to these different needs. Based on how processes are handled and the environment they run in, we can also talk about different broad types of process scheduling systems. One common type is batch scheduling. This was popular in early computers where users submitted jobs in batches. There was little or no user interaction. Jobs were collected, loaded into memory, and executed one after another. Scheduling was simple and often non preemptive. The system aimed to maximize throughput. For example, a payroll processing system might run hundreds of salary calculation jobs overnight without any user interaction. Another type is time sharing scheduling. This is what most modern desktop and server operating systems use. The CPU is shared among multiple active users and processes. Each process gets a small slice of CPU time, often called a time quantum. After this slice, the CPU is taken away and given to another process. This creates the illusion that everything is running at the same time. Time sharing relies heavily on preemptive scheduling. Imagine a computer lab where many students are using the same server. If one student runs a heavy program, it should not freeze everyone else's session. Time sharing scheduling ensures that each user gets regular CPU access, keeping the system responsive. Then there is real time scheduling. In real time systems, the correctness of the system depends not just on what result is produced, but also on when it is produced. Some tasks must be completed within strict time limits. Missing a deadline can lead to failure. For example, consider an airbag system in a car. When a crash is detected, the airbag must deploy within milliseconds. The operating system running this system schedules processes based on deadlines and priority. General fairness is less important than meeting time constraints. Real time scheduling can be further divided into hard real time and soft real time systems, but that is explored later in detail. Another perspective on process scheduling comes from understanding how many processes are allowed into the system and when. This connects scheduling with the idea of different schedulers, which you will study next. For now, it is enough to understand that process scheduling works closely with these schedulers to control system load and CPU allocation. It is also useful to understand that scheduling decisions are based on the state of processes. Only processes in the ready state are candidates for CPU scheduling. Processes that are waiting for I/O or have terminated are not considered. The operating system maintains ready queues and other data structures to manage this. Let us take a simple example to make this clearer. Suppose three processes are in the ready state. Process A is a text editor, process B is a view player, and process C is a file compression task. The scheduler looks at these processes and applies its rules. Maybe it gives each process a small amount of CPU time in turn. The text editor gets CPU time, then the video player, then the compression task, and then back to the editor. This cycle continues until processes finish or move to another state. To the user, everything seems smooth and continuous. One important thing to remember is that process scheduling is not the same as CPU scheduling algorithms, even though they are closely related. Process scheduling is a broader concept. It deals with managing processes and deciding which one should run. CPU scheduling algorithms are specific strategies used to make that decision. Later topics like first come, first serve, shortest job first, and round robin are examples of such algorithms. Another aspect worth mentioning is priority. Some processes are more important than others. The operating system may assign priorities based on factors like user importance, system tasks, or process behavior. A system process handling memory management is usually more critical than a background user application. Scheduling can take priority into account to ensure critical tasks get CPU access when needed. However, priority scheduling must be handled carefully. If high priority processes always run, low priority ones may never get a chance. This situation is called starvation. Operating systems use techniques like aging to slowly increase the priority of waiting processes to prevent this. In summary, process scheduling is the mechanism that allows an operating system to manage multiple processes efficiently using limited CPU resources. It decides which process runs, for how long, and in what order. It is essential for multitasking, system responsiveness, and overall performance. Different types of scheduling exist to suit different system needs, from simple batch systems to complex real time environments. As you move forward, you will see how schedulers are structured, how context switching makes scheduling possible, and how specific CPU scheduling algorithms work in detail. All of those topics build directly on the foundation of process scheduling. Without scheduling, an operating system would not be able to support modern computing as we know it. That is it for this video. See you in the next one.